Hello and welcome to the fourth lesson in the representing data unit. This time it's about representing images. We've already looked at numbers and text, now it's time for pictures. But first of all, let's see what you can remember of last week's work. Using this ASCII table, I'll disappear in a second so that you can see it. What word is encoded with that binary down there? Give you a few seconds on that one. I'll disappear, pause the video, have a go at translating it, and then unpause when you're ready. Okay, hopefully we're done. Well, let's find out what it was. That first binary number works out at 104, which if we look at it on the table here, is H. The next one is 97, which is A. And the last one is 109, which is M. So the word is ham. Right, so last week we looked at how to store text on a computer. Very straightforward method. We just use a lookup table to find a number to represent each character and then stored those numbers as binary. It turns out, of course, if we can represent anything at all as numbers, then we can represent it on a computer because we use binary to store those numbers. So for images, we just need to find a way to store an image as a sequence of numbers. Now there are several different methods that are used across the world for doing this, but the most common one is something called a bitmap, and that's what we're going to look at today. In a bitmap, the image is split up into a grid, and then each of those grid locations is filled with a single colour, the colour that best represents what's in that grid. So if we look at this picture here, and we cover it in a grid, and then we take each of those grids and fill it in with the colour that best represents what's in there, well, we end up with that. Very difficult to see the original picture of the dog there. But if we use more lines and make more locations in our grid, so start with the same picture, this time we'll have a higher number of elements in the grid, it starts to look a little bit more like it. You can sort of see that brown shape where the dog's going to be. And as we keep doing this, so if we add yet more grids to it, that becomes more like we can see the dog, and as we keep going with it, that's getting better and better. If I remove those grid lines, you can kind of see from there that this one here you would probably just about recognize as a dog. But it turns out those little grid elements are called pixels, and those are what makes up all bitmap images. Now the number of pixels contained within an area is referred to as the resolution. So a high resolution image is made up with lots and lots and lots of tiny pixels, or huge number of rows and columns in that grid, whereas a low resolution image is made up of fewer of them. So if we look down here at the bottom, a low resolution over at that side, down to a higher resolution here, you can see how the dog becomes clearer and clearer. High resolution images have more pixels and are much better to look at. So your first set of notes to make for this lesson. Could you make a note of the following in the book? To represent an image on a computer, it is split up into tiny sections called pixels. Each pixel is assigned a single colour, and the more pixel an image has, the higher its resolution and the better it looks. So make a note on that, unpause when you're finished. Okay, let's move on. So we know we need to now store a sequence of colours, because each pixel's in order is just this colour, this colour, this colour, this colour. So how are we going to represent those colours? Remember, we need to try and represent it entirely as numbers, because then we can store it as binary. So can we make a number to represent each different colour? Again, there are a couple of different methods that get used, but we're going to look at a very common one about mixing colours. Now, you've probably been taught in art that the primary colours are red, yellow and blue. That's actually not quite right. The three primary colours as far as art is concerned, as far as mixing paint and ink is concerned, are actually magenta, yellow and cyan. Now they're very close to red, yellow and blue, as you can see, and historically red and blue pigments were far more easy to come by than magenta and cyan. So red, yellow and blue were generally used as primary colours. You can get very close to most colours with that. But to be completely accurate, magenta, yellow and cyan are the three primary colours. Now, if you were to open up a printer and have a look at the cartridges inside, you'd find the colour cartridge consists of magenta, yellow and cyan ink, because those are the three colours that can mix anything else. But that's for mixing paint and mixing ink. It's not the same for mixing light. If we want to display colours on a screen, we're not mixing ink. We've got a tiny array of lights that shine, and it's the light colours that mix, and that's different. To mix light, our primary colours are red, green and blue. And if you were to stick your face really close to a screen, probably not a particularly high resolution screen, because you'd struggle to see them anyway, you would see there are an array of tiny red, green and blue LEDs or LCDs that emit light. And it's the mixing of those lights that gets us the colours. So that's how we can represent our colours as a number. By combining different intensities of red, blue and green, we can create any colour. And that's what we do. We store a number to represent how much red there is, a number to represent how much green there is, and a number to represent how much blue there is for each pixel. And then those numbers are stored as binary, and there we go. We've managed to represent a colour using binary, using ones and zeros. And if each pixel has its own individual colour in order, now we've got an entire picture stored using binary. So can we add to your notes the following? Each pixel of an image is assigned a colour. Colours are stored using red, green and blue, RGB, and a number for the amount of red, amount of green and amount of blue light in the colour is stored for each pixel. Unpause the video when you're finished with that note. Right, so a little task to have a go at. If you're on a Windows PC, which most of you will be, you can load Paint and do this. If you're on a different type of computer, there's probably an image editing software that will do a very similar thing. In Paint, along the top, you can click on this Edit Colours button, and this window will appear. Then what you can do, down there, you can input intensities for red, green and blue, and it will show you the colour that would result in. Now I've got some suggestions I'd like to have a go at. So red 0, green 255, blue 0. You can probably take an estimate at what colour that would be. The values down here range from 0 to 255 because they're 8-bit values and the maximum for 8 bits is 255. So if there's no red, there's maximum green and no blue, we would expect that to be green. So test it, put 02550 and see if that comes out green. What about this one? Red 255, green 255, blue. Putting full red, full green and no blue, what colour would that come to? Well, if we look back at the previous slide, there's a bit of a hint here. Look what happens when green and red are mixed. We get yellow. So presumably, by mixing full red, full green and no blue, we should get yellow. Try it out, see if that's right. What happens if you put maximum red, 0 green, maximum blue? Then try some other values. See if you can get the colour you're looking for. How would you get a orangey colour? We look on that chart here, it's a mixture of red and yellow. So if you put a lot of red and less green, see if that ends up with orange. Try a few colours, try mixing them, get the hang of how mixing red, green and blue can result in different colours. Nothing you need to write down or produce for this, it's just a bit of a play around and see what you come up with. So when you're done with that, unpause the video and we'll carry on. Okay, let's move on. The last thing we need to know how to do is to calculate the size of an image. Now we know how to take an image and store it as ones and zeros. How many ones and zeros do we need for a particular image? Well, we know that each one of those pixels has to have enough bits to store the amount of red, green and blue. And we know that each picture has a certain number of pixels. So if we take that number of pixels and multiply it by how many bits are needed for each pixel, that should give us a total number of bits. Well, let's have a look at an example. So this one down here, we've got an 800 by 600 pixel image using 16 bits per pixel. So 16 bits are used to store each pixel. What's the size of the image in kilobytes? There's a fair bit to this. First of all, let's work out how many pixels there are in our image. If it's 800 across and 600 down, we need to multiply 800 by 600 to get 480,000. There are 480,000 pixels that make up this 800 by 600 image. Great. Now each one of these pixels uses 16 bits. So we'll multiply that by 16 to get 7,680,000 bits in total for one relatively small picture. Well, that's the answer in bits, but it asks for the answer in kilobytes. So let's convert it to bytes. We have to divide by 8 to get the answer in bytes, which is 960,000. And then to get to kilobytes, we divide by 1,000. So 960,000 divided by 1,000 is 960 kilobytes. Okay, that's the most complicated thing we do in this lesson. If you can do that, great. If you're struggling a bit with that, get as far as you can with it when you get the question on it and see how we go. So the main task of this lesson is, as always, to complete the quiz on the VLE. There's a couple of very easy questions. There's one or two more difficult ones. Do the best you can. As always, you are allowed to use this video or the PowerPoint behind me, whichever, or your notes, whatever you want to use. This isn't a test. I'd rather you look up any answers, you find out the answers to anything you're not sure about. If you've done the quiz and you've still got some time left, there's an extension. If you go to that address on there, and if you go to the VLE and go to this task, there's a link to it in there, you can try creating some pixel art. It's a website that's designed to make art just by using large pixels. Try drawing your favourite animal, character from a movie, using these large pixels and see what pixel art you can make. When you've got a really good one and you're happy with it, submit your best drawing to the VLE. Okay, so there's a quiz and the extension to have a go at. Hopefully you managed to follow along with most of that. The calculating the size can be a bit complicated, but the rest should be fairly straightforward. And I'll see you all for next lesson.